Hello, my name is Jamie. My partner's name is Zahir, and we were assigned the counting sort algorithm.
So we start off with what is it? What is counting sort algorithm? In computer science, counting sort is an algorithm for sorting a collection of objects by a key, which is a small positive integer. That is an integer sorting algorithm. It sorts the elements of an array by counting the number of occurrences of each unique element in the array. So like whenever we want to keep track of an occurrence or add, subtract, we can use a counting sort algorithm. So on this slide, there's a little example of a counting sort algorithm. As you can see, it is color coded, so it is easier to keep track of where the numbers are going. So on the top, we could call this the data range. It's which is from 1 to 8. 1 is the lowest and 8 is the highest number. So the data range is from 1 to 8. And then the one below that in the middle, we could call this the indexes, where as you can see, since it's color coded, so the 1 is going with the first number, and then the 2 is the 2 in second place, and so on and so forth, the third index and fourth, fifth. And then in the bottom, the one all the way in the bottom, we could call this the final place, which is where all the final indexes and the numbers would go, and it would be in a counting sort algorithm. So how does counting sort algorithm work? Sorted count works by iterating through the input, counting the frequency of each element, and using those to calculate the index of the elements in the sorted array. So let's say we have an array with whole numbers from 0 to 10. The idea is to count how many zeros we see, how many ones we see, how many twos, threes, and so on. Since there are 11 possible values, we'll use an array with 11 counters, all initialized to 0. So the next step would be to iterate through the input once. The first item is a 4, let's say, and we'll add 1 to count 4s. The next item is an 8, and we'll add 1 to count 8s in the array. And so on. When we reach to the end, we'll have the total counts for each number.
In this slide, I'll be going over the example or steps that I have for a counting sort algorithm. So for the first step, I have find the max, which in the picture below, it would be 8. In the second step, I have make an array with all elements 0 to store the counts. So we would start at 0 for the array and then go to the max number, which in our example is 8. And in step 3, I have count each element in the array, which if we go back to step 1, the picture under it shows us that there is 1 4, 2 2s, 1 8, 2 3s, and 1 1. So all the other numbers that we have, like 0, 5, 6, and 7, would stay with the number 0. In our next slide, it would be a continuation. So here I'll be going over the steps we were going over in the previous slide. So in step 4, I wrote the store the sums of the elements in the array. So on the left, I have what was in step 3, just so we can see. And on the right picture, I have the actual sums of the elements. So if we go first, 0 plus 1 is 1, then 1 plus 2 is 3, and then 3 plus 2 is 5, and 5 plus 1 is 6, and 6 plus 0 is 6, and then do 6 for 5, 6, and 7, and then 6 plus 1 is 7. In step 5, I have find the index of each element of the original array in the count array. So in the picture below, you can see our array count and our output. And we see in the first number that it's 4, that we go into the index of 4 for the count and do 6 minus 1 equals 5. Go to the index of 5 for our output and put 4. And it works for all the other ones too. So for 2, we go to the index of 2 in our count. We see that it's 3. And for 3 minus 1 is 2, go to the index of 2 for our output and we see 2. So it works for 8 as well. And 8, it's 7. And 7 minus 1 is 6. We go to the index of 6 in our output and see that it's 8. For 3, we see in the index of 3 for our count, it's 5. 5 minus 1 is 4. Go to our index of 4, we see that it's 3. And for 1, we go to the index of 1, we see that it's 1. 1 minus 1 is 0. And in 0, we put 1. And yeah, that's basically how the count sorting algorithm works.
So where do we use counting sort algorithm? We use counting sort algorithms in many different ways. We use it when we want to keep track of a certain number in a code, or we can use it when we need to track values in a code, like how many times we say k or I. However, counting sort is generally only used if k isn't larger than I. In other words, if the range of input values is not greater than the number of values to be sorted. We could use it if we were to code an app that would track how many times we say the words like, or bored throughout the day or the week. For that, we would use a counting sort algorithm.
In here, I would be discussing the running times for counting sort algorithm. As we can see on the slide, the best case is O(n plus k). The worst case is O(n plus k), and the average case is O(n plus k). And that is because the time complexity of counting sort algorithm is O(n plus k), where n is the number of elements in the array and k is the range of elements. Counting sort is the most efficient if the range of input values is not greater than the number of values to be sorted. So that means that it works best when k is not significantly larger than n, as well as it works worse when k is larger than n. In this slide, I will be going over whether counting sort algorithm is stable. And I said, yes, it is stable, and that a sorting algorithm is said to be stable if 2 objects with equal keys appear in the same order in sorted output as they appear in the input array to be sorted. So in counting sort algorithm, numbers with the same value appear in the output array in the same order as the input array. So yes, it is stable.
Counting sort is not an in-place algorithm. Ignoring the count array still requires separate input and output arrays. In computer science, an in-place algorithm is an algorithm which transforms input using a data structure with a small, consistent amount of extra storage space. The input is usually overwritten by the output as the algorithm executes. As described, counting sort is not an in-place algorithm. Even disregarding the count array, it needs separate input and output arrays. It is possible to modify the algorithm so that it places the items into sorted order within the same array that was given to it as the input, using only the count array as auxiliary storage. However, the modified in-place version of counting sort is not stable.
So in this slide, I guess I'm going to be covering what's special or unique about counting sort algorithm. And I said that it has like lesser time complexity when range is comparable to number of input elements, and that counting sort algorithm has reduced space complexity if the range of elements is narrow, and that is more frequency of close integers. Okay, that was the last slide, and that's everything we have about counting sort algorithm. So thank you.